Hi, welcome to ustudy.in and this is Lakshmi Anand. In this session, we shall see about the block diagram of a PLC. A PLC, in fact, is actually a microcontroller application. The PLC contains a microcontroller, and in fact, PLC is a microcontroller with specific application in the industry. So here in this block diagram of a PLC, we have this gray area which actually is the PLC. So inside this we have marked out areas which are functional block diagrams of the PLC. See, you may not be able to find them in real blocks like this inside a PLC. What you may actually find is just one or two ICs, but actually these are the functional block diagrams, functional blocks of a PLC. Here we have the first one as the CPU. This is the central processing unit, as you might know. See, the CPU of the PLC will be a dedicated microcontroller or a microprocessor, the design of which and the selection of which differs from a manufacturer to manufacturer. This CPU essentially processes the information which comes into the PLC according to the programs given to it and controls the output accordingly. See, this is the read-only memory which teaches the CPU, which probably knows just a few machine code, how to run user programs and how to interact with various other devices. This program on the ROM converts this CPU to a PLC, and the code on this ROM will probably be written by the manufacturer of the PLC. And then we have this RAM, which, as you know, is random access memory, which is used to store various variables during the running of the PLC program. Maybe what is the status, what are the internal variables, what are the internal timer values, and so on. And this is EEPROM, which is almost nothing other than EEPROM nowadays. It is just electronically alterable programmable read-only memory or electronically erasable programmable read-only memory. This EEPROM is used to store user data that must not be lost when the power is turned off. Values of timers that must not be lost. It can contain configuration variables. It can contain any data that the program specifically specifies that it must be saved even when the PLC is powered off. And then we have this programming port. Every PLC is reprogrammable. The logic with which the inputs and the outputs are connected is defined by this program, and this program can be reprogrammed on the field. This is exactly what makes a PLC useful. So this programming port enables the CPU or this PLC to communicate with various other programming devices through which you probably program the PLC. Most probably nowadays you will be using a computer or a laptop device. So the computer can be connected to the PLC, most probably using an RS-232 communication port, or nowadays using a USB port. There are PLCs which require proprietary connectors. The connectors are non-standard. For them, you will have to contact the manufacturer of the PLC for getting the cable or the converters required to connect the computer with your PLC. And then there are these handle terminals which you can use to program the PLC. They will be pretty much useful if the PLC is inaccessible or you don't want to carry around a laptop. But nowadays they are increasingly being replaced with small laptops. And then we have this internal bus. As you know, in any computer system, various parts communicate with each other using an address and data bus. And since a PLC also is nothing much different from a microcontroller system or a microprocessor based system, it requires an internal data bus with which it communicates with various other devices which we'll see shortly. So all these components on the left hand side to the internal bus are the basic things required for a PLC to work. First is the CPU, which actually does all the processing, and then various types of memory devices which store data either permanently throughout the life cycle of a PLC, as in the case of the ROM, or just temporarily for a few, just temporarily until the PLC is powered off, or maybe an EEPROM which stores the user data even when the device is powered off. and the programming port. These are to the left side of the bus. To the right side, what we see is sort of like in the input-output system of the PLC. See, this input-output system of the PLC is what makes a PLC much different from a traditional computer or a simple microprocessor. See, this interface is industry friendly. They accept industrial voltage levels, they are noise proof mostly, and they support connecting industrial devices like bulbs, motors, contacts, relays, switching devices, etc. They can be easily connected. All industrial devices can be connected to a PLC either as input or as output as the cases. So this input output system is very robust. So this industrial customization of this input output system of the PLC is what makes a PLC very special. So first we have the digital input output interface. So any PLC will contain a minimum amount of digital input and output, as this is very essential. So by digital we mean that the input can either be turned on or turned off. That's it. Either it is 0 or 1, it is on or off. That's it. So this digital input outputs are differentiated into various types depending on the basic electronics that produce the output. For example, in the case of the digital input, there are two voltage levels supported by a PLC. A PLC may support DC voltage inputs or it may support AC voltage inputs. So it is very rare to find a PLC which supports both DC and AC voltage inputs, but depending on the PLC model, it is either DC input or AC input. For example, you give it a specified DC voltage range, and if the voltage is supplied or available or present, the input is considered to be turned on. For example, let us say 24 volt DC. If the 24 volt DC is present, the input is considered turned on. If the 24 volt DC is not present, the input is considered turned off. So the AC voltage input is also very same. You can probably connect a 230 volt input, and if the 230 volt input is given in, it is considered on, that is high, that is 1, or if it's not present, it's considered 0. Now let's move on to the digital output interface. There are again various types of output interfaces depending on what exactly the PLC utilizes to produce the output. If the PLC contains an internal relay to produce the output, so that's called a relay output. If the PLC uses transistors to produce outputs, which is very essential in the case of fast switching, we have transistor outputs and then we have track outputs to connect to AC output devices directly. And then here we have various other interfaces, we should call them, because their interfaces might be optional and depending on the PLC model may be available or may not be available at all. Now these digital input and output interfaces will be mostly available most of the time, 99% of the time, but these things are optional. They may be present in the higher end models, they may not be present in the lower end models. It depends. So we have analog input output interface which accepts an analog signal. So an analog signal will probably be a number, a pressure, distance, temperature. An analog input will accept a signal as a voltage or current in a larger range. So it is not just 0 or 1, it is a value like 1, 2, 3, 4, 5, 6, 10, 20. So it can be anything in between. A pulse counter and timer interface enables the PLC to communicate with very fast high speed digital pulse inputs, for example maybe a rotary encoder. So it is just a high frequency pulse which the digital interface may not be suitable for handling. And then we have additional digital input output interfaces which might mean things like high speed inputs or dedicated digital control systems which do specific things like controlling a servo motor or maybe specific devices. And then we have this communication interface. A PLC in the industrial floor must communicate with various other devices on the industry. Might be other PLCs they may be computers, they may be sensors or display devices. So the most commonly used communication interfaces in a PLC are Modbus, Profibus, CAN network, Ethernet, or other proprietary networks. So using these, various devices can communicate with the PLC, exchange data, maybe extend the control function, maybe control a lot more devices, and so on. I hope this session was useful for you. Maybe it was too long. Thank you.